Record. Alrighty. So the first order of business is to parameterize the surface, which in this case is the cylinder. And so the normal way to do that is to use two variables. In the XY plane, it's just a circle. So we can get away with just doing 2 cos theta, 2 sine theta, and that'll take care of the circular part. And then for the up and down movement, I'll just use Z. I'm not going to alter that. But the bounds become important. The theta bounds are, and of course you can use U and V. I know that the tendency is to use U and V in this manner, but you want to get a full circle, so 0 to 2 pi, and then Z, well, what we do here is solve for Z. We get 2 minus x minus y and 7 minus x minus y. So your Z bounds look like this. And that gets us our parameterization. Um, you need to go through the rigmarole of figuring out, well, first of all, okay, my bad. Let me continue on here. Your vector field now can be converted into this notation. So remember, when you do the parameterization, you're actually creating formulas for x, y, and z. So that's x, this is y, and of course that's z. So uh, the vector field now is just x, which is 2 cos theta. And this one, because this is kind of like the identity vector field in a way, it doesn't really change much. It's kind of frustrating. So this will be your vector field now in terms of the parameterized variables. And then you have to go through the trouble of working out um, the so we call this the R, or I guess the surface R. So you have to do R sub theta and R sub Z. So let's do R sub theta. I'll show you the steps. It looks a little rough, but it's not too bad. It'll be negative 2 sine theta. You're taking derivatives, 2 cos theta, and 0. R sub Z will actually just be 0, 0, and 1. So when you perform their cross product, and I'm making sure yeah, don't want to lose my spot there. Um, it's not too bad. I should give myself more room because um, well, let's see, you just get 2 cos theta. J, you'll get 2 sine theta, and the K, you'll get 0. Okay. Um, well, that's kind of nice because now you can do F dot. You dot these two. So let me circle them. Take this guy and this guy, and you dot them. So here's what you have here. You've actually created a normal vector that sticks straight up out of the surface when you do this step right here. And you're trying to compare the normal vectors that are normal to the surface with the actual uh, vectors of the vector field. And you're basically comparing how much they agree with one another. The dot product is essentially a comparison thing. If the dot product is positive, they generally point in the same direction. If negative, they're obtuse, and if zero, they're orthogonal. So if we do F dot this right here, you're going to get 4 cos squared theta plus 4 sine squared theta, and then you're just going to get 0. Well, that's nice because you just get 4. All right, that seemed a little too easy. Uh, no, I think that's what works out. All right. So let me pause there for a moment because really the rest of the problem is just kind of a quickie calculation. Does it make sense what I did here? I can scroll up to the top.
Yeah, it makes sense to me now. It's the problem always for me. This the what do you parameterize? How do you do it? How do you set your limits? From there, plugging that back in and getting the final answer. is
Yeah.
not difficult. It's just that it's that initial what do I grab and where do I put it? So no, it makes a lot of sense now.
Okay. Does anybody else have any questions on this one? I mean, I'll finish it off, but does it make sense what we're trying to do here? Again, really, in any of these problems, I mean, just parameterize that should at least get you started. And this gives you some X, Y, and Z items to play with. That allows you to rewrite F in terms of parameterized variables, which, and again, I'll admit in this case, we get the same vector field. We get the same thing as we got for R, which is not always going to happen. This is kind of a fluke, but that's what it is. The you take the partial derivatives and their cross product, and that gives you basically the n vectors, the normal vectors to the surface. And then this is the comparison of the vector field and the n vectors. And we got, quote, lucky because cos squared plus sine squared is 1. So it ends up just being a double integral. Let's see, it's going to be 4. And I think it probably just makes sense just to use, I guess I would just go dr d theta. Well, actually, you know what? I'm just going to go with what I had here. I had I'll just go d theta, dz d theta. That's a good one. Yeah, so theta, way back up here, where is it? Right there, 0 to 2 pi. And then these bounds right here are the bounds down here on this integral, the z integral would be these guys right here. But we don't want to write x and y anymore, so we have to take that. So it's going to go 7 minus, it'll be 2 cos theta minus 2 sine theta. And this will be 2 minus 2 cos theta minus 2 sine theta. And it looks like a mess, but it actually isn't. Here you get 4z, and you plug in the bounds, and then you get 4, and I'll show you, you'll see what happens here pretty quick. It's going to simplify pretty nice. And then minus 4, and then with this, with the 2, I have to just keep my stuff straight here. So you get 28, that's going to be 8 and 8, so 28 minus 8 cosine, that'll be plus 8. Yeah, see, that's exactly what happened. Check this out. You get negative 8 cos theta, and then here you get positive 8 cos theta. You see that? So actually, the only thing that survives is the 4 times 7 and the 4 times 2, and that gives us 20. And so as far as the z integral is concerned, um, all these guys just dropped out. And then you just do the outer integral, and you get 40 pi. All right. Um, all right. Did that help or hinder?
Well, that was absolutely help to me.
Okay. You know, I'm thinking, something has occurred to me. I think there's a faster way to do this. Let me give it some thought here. There's This is a flux integral through a closed solid. Now the solid is basically a cylinder with sloping sides. If I were to draw it, it'd be like taking a cylinder and then slicing it at an angle so you get like ellipses. In this case, because we're going between 2 and 7, the thickness would be 5. Now the cylinder itself is formed by moving a circle of radius, in this case 2. And so the volume of this object should be the area, which is 2 pi r, I'm sorry, pi r squared, so 4 pi times the thickness, which is the 5. And the only other thing that I wanted to do here, I need to think this out. So that's why I'm kind of doing this as I go along. Um, the divergence theorem, what you do is you take the divergence of the vector field. And the divergence of the vector field in this case, if I write it out, it's div f. It's basically the partial derivatives with respect to x, y, and z respectively, and you just get 3. 1 plus 1 plus 1 is 3. And so basically you get a triple integral 3 dv. Well, with 3 as a constant, you can factor that out to the front, and I get 3 times the volume. And so here I got 20 pi. So here I'm getting 60 pi as my answer. And I wonder if I made a mistake somewhere along the line. Um, I don't think I did. Again, I'm doing this kind of quick, so uh, double check my math. That's 28. That's minus 8, so 20.
40
See
pi
that.
is listed as the correct answer on this
40
one.
pi.
Yeah.
All right, then maybe my mistake is over here somewhere. Okay. Uh, yeah, I might need to give this a little more thought because it seems like it should work out. So I think I'm missing something over here. I'll tell you what, just kind of ignore that for now. But I am going to think on that. If I think of something, I'll let you guys know. I'll send an email because it should work. It's an enclosed object. I think the problem might be is maybe the volume isn't actually just space times thickness, but it should be. Gosh darn it. All right. Well, anyway. All right. Well, that's how you do it. We got the answer. So it's 40 pi. All right. So we have vector field F. Yeah, it's kind of bizarre looking. 18 XYZ plus 2 sine X, 9x squared Z, 9x squared Y. You're trying to find a function such that its gradient is the vector field. Okay. And of course, I guess I want the origin to be 0 as well. I'm going to stop the share. So this would imply that the vector field is conservative. I'm going to show you an extra calculation here. So the question is vector field F conservative? That's a fair question because if it's not, then trying to do this little maneuver is pointless. And you do that by showing curl of the vector field is 0. If the curl of the vector field is 0, then, well, that's a minimum condition for being conservative. It almost always means it's going to be conservative. So I'm going to go ahead and show that because I think it's probably good to review. Um, you set up your normal cross product and your partial derivatives, and you just pop these guys into place. And then I'm going to run through the calculation. So for the I component, it's going to be the determinant of these guys. So this means take the partial with respect to y of this guy. So it's 9x squared. And I'll tell you what, I'll do this as I, and then j, and then k, because it'll just be easier. So it'll be 9x squared, and then partial with respect to z, this will be 9x squared. So that looks like it's going to drop out good. For the j, we cover up this thing. We do partial with respect to x of this guy, which is 18xy. And then partial with respect to z of this guy, which is 18xy. Notice that 2 sine x just drops out. And then now we do it with k. Partial with respect to x here is 18xz minus, and then we do partial with respect to y of this, which is going to be 18xz. And then again, the 2 sine x doesn't factor. So sure enough, we get the 0 vector. Okay. That indicates that the vector field is likely conservative. So what you do, and I'll show you a couple ways, you basically integrate each part with respect to their x, y, and z. So the first component with respect to x, the second component with respect to y, and the third component with respect to z. Okay. Um, I'll do the bottom one here just to illustrate something. Really what you do is, but in this case, it's just going to be 9x squared y z plus a constant. And I'll just put an underline. You have to remember that you're integrating with respect to z, so there may be some terms here that don't contain z. So I'm going to leave this open as just kind of a blank spot. But you know what I'm going to do? I'm just going to go up to these guys and perform the same maneuver. The antiderivative here with respect to y is 9x squared yz. All right, that's nice. And here with respect to x, it's going to be, well, here you'll have 1/2 x squared, so 9x squared yz. Then you antiderive that, you get negative 2 cos x. And what you end up doing is you end up just looking at what your set of terms, and basically your potential function is these terms. If they're listed at least once, you include it, but you don't write it more than once. You'll notice that the 9x squared yz is present in all three, so just write it once. This guy was present in one of them, so write it once. And that's the generalized potential function. You can check that by taking its partial derivatives with respect to x, y, and z, and you should get the original vector field. Okay. As far as making sure that the origin gives you 0, you just plug in. Well, let's see what happens when you want that when f of 0, 0, 0 is 0. You plug in zeros, that just drops out. You get negative 2 cosine 0, which is 1, equals 0. Okay, I should have included constant integration. I could just do that, just call it k. So k would plus k would have to be 2. So it looks like just shove a 2 in there, and that should do the trick. There you go.
That is a
And
way better and a way faster setup than what I was doing.
well, there's a formal way to do this, and then there's an informal way. This is a little more informal, but unless you're getting, honestly, for the functions that we play with, this works. The deal with showing that the curl is 0 is that it's really just a minimum condition, not necessarily a sufficient condition for conservativeness. But the reality is that for the functions that we play with, it invariably implies a conservative vector field. So you're verifying that it is conservative by showing that the curl is 0. And then you kind of go through here, and then you just simply, again, anti-differentiate with respect to x, y, and z down here, and then just assemble your potential function by basically including it one of each term at most once. So you can see how I did that.
That is excellent. Thank you.
Sure. Anybody else have any questions on this one?
Test, except this one is 18 questions, if I remember correctly.
Yeah, it's a little longer. It's going to be heavily weighted toward the most recent material. Um, it's not a final in the usual sense. It's not a cumulative final. However, it is ostensibly weighted more. So in the syllabus, it said I think it was 30%. What I end up usually doing is I usually end up just weighting your best score at 30%. So basically, just treat this as like test 3. That's how I've labeled it in Honor Lock.
Okay.
Yeah, it's the same protocol. It's going to look like a normal like test that you've seen already. So it won't be anything special about this one. Pardon me.
And I'm guessing it's following the same protocol of if the practice exam is easy, the exam will be easy. which I would agree with.
Yes, yes. If you do the practice exam, you will see you'll see the questions. Um, so yes, do the practice exam a couple times. That gives you a good indication of what to expect on the final on the test three. Um, regarding the practice test, I know there have been a few questions that just aren't they're misprogrammed or something. That's extremely frustrating. I've sent them to the programmers to take care of it. I don't have access to the code, so I don't know what the timeline is on this.
They seem
All
to
I,
have cleaned up some of the yes no questions, and
yeah, but they
I think
messed
they got rid of that one question that doesn't have a box for the one blank.
they
That
messed
seems
up
to have
one
been.
too. In other words, it was one to show a conservative. Um, it was an R2, and they messed that up. So they fixed it and then messed it up. Oh, I'm so frustrated. So I sent it off again, said, "Hey, you guys got to fix this." So hopefully it gets done ASAP. I hope this doesn't happen on the test. All I can say is that if you get some crazy like error screen, just move on. I will take care of it. Forgot to unrecord the recording. So this is a half a sphere because x goes from 0 to 7. So it's looking to me like you've got basically got a half a sphere, everything to the right. This is not a good drawing, I'll admit. So it's basically half a sphere. It's everything to the right of x equals 0 on the x-axis. So that's really the trick, is to try to identify the picture, because you've got a bottom half of the sphere and the top half. That's what these guys are. And then when you look at the XY plane itself, you've got a bottom semicircle and a top semicircle. That's what these guys are. And then x goes from 0 to 7. That's what this guy is. And so this is a half a sphere. And so what we're going to do here is we're going to use the rho theta phi conversions. The rho is your radius, so that's going to go from 0 to 7. The theta is going to be the sweep angle in the xy plane, and you always want it to increase. So we're actually starting here at the negative y-axis, so it's going to go from negative pi over 2 to positive pi over 2. And then the phi is your what I call the equilibrium. It's when it's straight up, it's 0, and when it's straight down, it's pi, because that's 180 degrees. So your phi angle is actually kind of going this way from the z-axis. It's going to go from 0 to pi. Meanwhile, your integrand, we can replace that x squared, y squared, and z squared with rho squared. So we get 1 over radical rho squared, which is just 1 over rho. And meanwhile, you've got the Jacobian. So you've got a lot of things going on here. The Jacobian is rho squared sine phi. And so when I piece it all together, there's a d rho d theta d phi integral. It's going to be 1 over rho times rho squared sine phi. And the bounds would just be 0 to 7, negative pi halves to pi halves, 0 to pi. And then, of course, you can simplify this even a little bit and just call it phi. I'm sorry, rho sine phi. Okay. That's the setup. Does that make sense?
Absolutely. The negative pi over half or pi over two and then pi over, or yeah, the bounds were like throwing me for theta. I was doing 0 and 2 pi.
Okay.
Um,
Yeah, theta's still in the XY plane.
mhm.
Um, Yeah, and
Drawing
those ones,
it out like helped to visualize it better.
yeah. Um, it's actually a pretty easy integral, so it is true that it simplifies rather nicely. In this case right here, integrating rho just gives you 1/2 rho squared. When you plug in the semi, you get 49 halves because the zero just drop it out. But then the rest of it's almost silly because then when you integrate theta, you just get pi halves minus negative pi halves, which is pi. And then you have to do the one last integral with sine, which is, I'll just do it here. It's actually going to be negative cosine theta from pi to 0. And when you plug in pi, you have to just watch out. Cosine of pi is -1. Then we have minus this negative here, 1. So you got 1 plus 1, which is 2. All right, how about that? So you've got 49 halves times pi times 2. Boom, boom. You get 49 pi. So believe it or not, this nightmare integral works out just to be that number.
Wonderful. Thank you. And it did
Sure.
work out. It was just like I said, getting the bounds. I think because I wasn't fully visualizing it, I knew like in a sense what it was, but I didn't put it actually like down how you drew the picture out, which helped with the theta and everything. So thank you.
Sure. Any other questions on just setting these guys up? I'll mention that you were debating whether to do spherical or cylindrical. Really, the answer is almost kind of tautological. If it's a sphere or part of a sphere, use spherical. If it's a cylinder or part of a cylinder, use cylindrical. And the way to recognize that is that like something like this, and I guess this just kind of comes down to just recognizing what the functions are. Um, in the one case where you mentioned that you had constants, and then just a couple of radical parts, that sounds like a cylinder to me. And in that case, cylindrical would be the way to go. I won't do it. I'll just mention it. I think this is the one you were asking about. This one right here. Yeah, this you can tell like if I do the y equals, these are going to be parts of a circle. In fact, this is going to be the lower half of a circle, the upper half of a circle. And then the x going from -7 to 7. This is actually a full circle. These two inner integrals together, the dy and the dx are making a circle. Or yeah. And then the z part just moves that circle up and down. That's where you get the cylinder. So in this case, this would be cylindrical coordinates. You would trade the y and the x for r and theta, and frankly, just leave z alone.
Got it. Okay.
Okay. And this guy, as I'm looking at it right here, this one looks bad too. It looks like a heavy duty, but when you do the substitutions, this is going to clean up. This will clean up real nice. And
That one did clean up very nicely, actually.
yeah, it's got constant bounds, and the beauty of having zeros and pies and 2 pies and stuff like that is that when you're integrating with the sines and cosines, a lot of them just drop out or become 1. So the calculations tend to be, ironically enough, pretty mundane, ironically enough. All right. All right. Um, well,